So in this first introductory section, we're going to show how utilizing polar coordinates can be very beneficial to evaluating some more difficult integrals by converting from Cartesian into polar coordinates. Before we can do that, we have to start with the most essential, the fundamentals of being able to convert. And we're going to not use a Cartesian rectangle, but we're going to be utilizing this thing called a polar rectangle to be able to evaluate a volume. All right, so a polar rectangle is just going to be essentially a sector. And you may remember from elementary geometry or trigonometry that the area of any sector is pi r squared theta. All right. Now, the goal is to be able to get theta infinitely small. So in other words, we want theta approaches 0. Okay. Or another way to think about that is the limit of the number of polar rectangles that we're going to construct are going to be infinite. So if you notice, what we're trying to do is we're going to take this polar region, all right, so a circular region, we're going to divide it up into a number of polar rectangles. Now I want you to notice that in this diagram B, that the rectangles are not truly rectangles. There's a little bit of curve, but we're trying to approach infinity. To go from one radius to the next, we have this r sub 1, r sub I, and r sub I minus 1. To go from one angle to the next, that's theta sub I minus 1. Well, what we can do is we can substitute r as the distance between the radii, so that's going to be r sub I squared minus r sub I minus 1 squared. Delta theta is the change in theta. Now notice that we can factor. All right, so we're going to take this and we're going to factor it. All right, and you might recall that r sub I and r sub I minus 1, let's just define that as 1/2 r sub I minus 1 plus r sub I. So in other words, we're going to substitute that back in for right here. And that's just going to be our r sub I. So in other words, what we end up with is that the change in theta is going to be r sub I asterisk. Okay, so that's just going to represent our change in the radius, r sub I minus 1. Excuse me, that's going to represent, let me go back just a moment. That's going to represent this. Okay. The change in the radius, delta r, is going to be r sub I minus 1, and then delta theta is just going to be delta theta. So whenever we convert from Cartesian into polar coordinates, we're going to have a multiplier. And the multiplier we're going to change, and we recall that there is a change. So remember that x is equal to r cos theta. Y is equal to r sine theta. So we're going to have to use those changes. So that's this right here. And then we have this r dr d theta. That's the multiplier. That's a result of all this algebra up here. Okay, so r dr d theta is really that r sub I asterisk, which is r plus r sub I minus 1. R sub I minus r sub I minus 1, the difference between the radii, that's going to be delta r, and then the difference in the angles, delta theta, is going to be d theta. So we can take a look at an example as to where this is going to be extremely easy. All right, and one other representation, don't forget that in polar coordinates, x squared plus y squared is r squared. All right, so we want to have those three formulae on hand so that way we can work our problems. A very simplistic example of this. Let's say we have the integral, the double integral r, where r is the region, xy dA. R is the region bound in the first quadrant, bound between two circles. X squared plus y squared is 4, x squared plus y squared is 25. You can imagine that if we were to solve this, we would say that y would be equal to plus or minus the square root of 4 minus x squared. and that y would be equal to plus or minus the square root of 25 minus x squared. Immediately, we're probably looking at a trigonometric substitution to be able to evaluate these in Cartesian coordinates. All right, we don't want to do that. A much easier way is to be able to utilize our polar coordinates. So let's try to get everything in terms of r and then think about what's going on with this. Okay, so I'm going to draw a picture. Okay, x squared plus y squared is 4 in the first quadrant. All right, so that's a semicircle of radius is equal to 4, or r squared is equal to 4, since x squared plus y squared is 4, okay, which means that r is going to be equal to 2. We have another radius. R squared is 25, and that's from right here. We know that r squared is 25, which implies that r is 5. All right, so here's what we're looking at. It's obvious that the value of r, the radius, is going to range from 2 to 5. All right, and if you can imagine it, these are like our polar rectangles that we talked about before. We're just breaking those up into an infinite number of polar rectangles, and then we're just going to add those up, Riemann sum the double integral. The next thing we need to figure out is what theta is. Well, theta in quadrant 1 is 0 to 90 degrees. All right, so if this is 0 degrees, and then we just go ahead, so theta is 0, and then up here, theta is pi halves. All right. So now we can set the double integral up very nicely. All right, so our double integral of the region R of xy dA is now going to be equal to 0 to pi halves, and then from 2 to 5. Notice that x is going to be equal to r cos theta. Y is going to be r sine theta. Then we also need that multiplier. Okay, we need this every single time that we convert. R dr d theta. Okay, so we can't forget about that. And again, that's a result of the conversion. Okay, so go back a few minutes and take a look at that conversion. I'm going to rewrite the integral now. All right, we're going to rewrite it, and I'm going to rewrite it in 2 steps. So we have integral from 0 to pi halves, 2 to 5, excuse me. We have an r, we have an r, and we have an r. That's r cubed. Then we have sine theta cos theta. And then we have dr d theta. All right. Now, I want you to notice that both of the bounds are constants. Okay, in fact, all of the bounds are constants. If all of the bounds are constants, meaning that we don't have any variables like we did in the previous section with most of the problems, then what we can very easily do is we can just go ahead and separate them into 2 separate variables, or 2 separate integrals that are being multiplied together. Again, this only works if we have only constants. All right, so I'm going to separate this, although you don't have to, but it might be helpful. I'm going to separate this into 0 to pi halves, sine theta cos theta d theta, times the integral of r cubed dr. All right, and that's from 2 to 5. Again, we can only do this if we have constants for all 4 of the bounds. If any of the bounds are variables, we have to utilize the technique that we used in the previous section. All right. Notice for the first factor of the integrals, we can just use a u substitution. U is sine theta, du is equal to cos theta d theta. So that's going to change our integral from a to b. Wherever we see a sine, we're going to make that a u. Wherever we see a cos theta d theta, that's going to be du. Now we still have 2 to 5 of r to the third dr. So there's nothing we can do about that because everything's in terms of theta that we're doing the substitution for. No big deal. We're going to evaluate. So now we get u squared over 2 from a to b. We also get r to the fourth over 4 from 2 to 5. These are being multiplied together. We're going to back substitute. So now we're going to get sine square of theta over 2, 0 to pi halves. And then we're going to have r squared over 4 from 2 to 5. We're going to substitute by utilizing our fundamental theorem of calculus. So now we get sine square pi halves over 2 minus sine square of 0 over 2 multiplied by 5 square, or 5, excuse me, we have to go back up here. This should be a fourth power. I apologize. Copy error. Right. So that's going to be 5 to the fourth over 4 minus 2 to the fourth over 4. Right. At this point, it's evaluation. Not too difficult. Sine of 0 is 0. So that means sine square of 0 is 0. So that goes away. Sine of pi halves is 1. So we end up with 1 square over 2 minus 0 over here. 5 to the fourth, 5, 25, 125, 625 over 4. And then 16 fourths is obviously 4. I'm just going to leave that as 16 fourths. Right? That works out to be 1/2. 625 minus 16, that's going to be 609 over 4. 609 does not contain a factor of 2, so this just winds up being 609 over 8. So a very elementary introduction to being able to utilize polar coordinates to evaluate these sorts of double integrals. We're going to see these a few more times, all right, but go back, take a look at both the theory of how this works with the polar rectangles, and then also take a look at being able to implement this correctly. Don't forget your r dr d theta as your multiplier.